Welcome to the second P4 revision video for explaining motion. This covers syllabus points 4 to 7 and 10, distance time and displacement time graphs. Okay, so in the first video we talked about distance and displacement and what they were, and now we're talking about the graphical representation, and it's worth getting an overview of this to start with. There are 4 graphs that if you're doing higher you will need to know about, and for foundation you really probably only need to know about 2 of them. So distance time graphs, displacement time graphs, speed time graphs, and velocity time graphs. Every single one of them has time on the horizontal axis and one of the other 4 quantities on the vertical axis. So a really important thing to get into the habit of doing when you're looking at these graphs is to make sure you look at what is on the vertical axis, what's on that y-axis, okay? Because the interpretation of the graph is hugely dependent on what's there. If you don't check to start with, you'll just start off on the wrong foot. Okay, so we're going to start with distance versus displacement time graphs. If you remember from the first video, distance is how far we've travelled during a journey, and displacement is how far we are from our starting point. So we're going to plot the 2 graphs together for one journey, and the journey is represented by the little blue blob down the bottom here, which is going to move along, and a red line will appear on the graphs to indicate what's going on. So if we play this along, then you can see that the blob is moving along, and it moved very quickly to start with, away from its starting point, and both distance and displacement increased. It then stopped for a while, which is this horizontal section on both graphs, and then it moved slowly back towards where it started. And we talked before about the fact that distance can only increase, so the distance graph is always increasing, but because it moved back to its starting point, the displacement graph is, the line is going down again. So you can see we said steep is fast. That's a good characteristic of these graphs, is that the steeper the line is on a distance time graph or a displacement time graph, the faster the motion, and the blob is moving very quickly to start with. Horizontal line on either type means it's stopped, it's not moving, the distance remains constant or the displacement remains constant, so there's 0 speed there. And a shallow line, so a shallow gradient, means that we're moving slowly. You could see the last section of the journey, the blob was moving quite slowly. And we get additional information from the displacement time graph because it can slope down. The distance time graph will always slope up because distance always increases. Sloping up on a displacement time graph means we're moving away from where we started, and sloping down means we're moving back towards our starting point. Okay, so that's the basics of those 2 graphs compared to each other. And the key summary there is steeper slope is faster movement, steeper slope or steeper gradient, and also a straight line is constant speed. All the motion in that example was at constant speed. So we've got this slightly unrealistic idea of these sharp edges, these sudden changes in speed, which aren't going to happen in reality. They'll be smoothed off, okay? So what does it look like if we have a slightly more realistic distance time graph of changing speed? This is really higher tier only. Instead of those sharp changes, we're going to get a curve. So here we're going to see the blob accelerate up to start with, so it will speed up, and then it will go at a constant speed for a little while, and then it will slow down at the end, and you can see how the graph works for that. So we're getting steeper and steeper as we speed up, and then as we slow down towards the end, it gradually smooths off and levels off the slope. Okay, so getting steeper is increasing speed or accelerating, and getting shallower is decreasing speed. Right, and the straight line section, it's kind of difficult to see it, but that middle section is straight line, is constant speed, as we've already said. So if you see a curve on a distance time graph or a displacement time graph, that means the speed is changing. Okay, so the displacement time graph, this can cause some confusion. Because displacement can decrease again, we've got to deal with, well, what does getting faster and getting slower look like on this? Well, the same rule applies. Okay, even though the line can slope downwards on a displacement time graph, showing that we're going back towards our starting point, the steeper equals faster rule still applies. So this first section here, even though it's sloping down, it's getting steeper, so speed is increasing. Okay, and this second section, it's getting shallower, so the speed is decreasing. That's for a displacement time graph there. Okay, and the last thing here, before we do some questions, the velocity from a displacement time graph. Okay, now we'll talk in future videos about exactly what velocity is, but a bit like displacement, it's got a direction. So distance doesn't have a direction, direction displacement does. Speed doesn't have a direction, but velocity does. They kind of go in these sort of pairs. And because the displacement time graph can give us information about which direction we're going in, we can also get information about the velocity that it's not possible to get from a distance time graph. So if you're asked about velocity from a distance time graph, you can't tell. You can only tell the speed from a distance time graph, not the velocity. So, again, we'll look at our standard journey, the same thing we did before. Replot the graph just to remind you. So fast away from our starting point, level, and then back towards it. And again, sloping up means away from the start point, so that's positive velocity. Remember we said that the original direction you go in, we usually say is the positive direction. So as we're moving away from our starting point, we have positive velocity. And then in the last section, as we're moving back towards the starting point, we have negative velocity. Okay, so time for some questions now, just to have a go at applying the ideas we've learned. So pause the video, have a look at the questions. You're going to answer some questions about the labelled sections from the two graphs. They are completely unconnected. One is a distance time graph for one journey. One is a displacement time graph for a totally different journey. So have a look at the questions and see if you can match up which sections go with which questions. And then we'll check in a second. Okay, so let's have a look at these graphs then. Looking at graph 1 to start with, well, what we've got then is the following. So which sections show the same speed? Well, the speed, remember, is the steepness of the graph on this time graph. So sections B and D are kind of parallel to each other. They are about the same slope. So B and D will be at the same speed. They're certainly the closest for that graph. The highest speed is the steepest part, so A is the steepest part of graph 1. Object being stationary, so it's not moving, is the horizontal line, which is C. And then which sections show positive velocity? Well, this was kind of mean, it was a trick question. It's a distance time graph, graph 1, so we cannot tell which direction we're moving in, and therefore we can't tell which are the positive velocity sections. We can only tell about the speed. And then if we look at graph 2, over here now, the displacement time graph, which sections show the same speed? Well, trickier. Remember, speed, it doesn't matter which direction we're going in. So A and B are about the same slope. Even though A is sloping up and B is sloping down, they are the same sort of steepness. And so they both show the same speed, even though the object is moving in opposite directions. Okay? They're the same speed. The highest speed, well, D is the steepest by quite a margin there, so that's definitely the highest speed. The stationary, again, is section C because it's the flat part, it's the horizontal part of the graph. And then positive velocity we can tell from the displacement time graph. It's the sections where the graph is sloping up in this case, so A and D are the two upsloping sections there. Okay, so some more questions for you to have a go at. This time it's matching some displacement time graphs to 4 different scenarios. So you have to say which letter goes with which number graph here by looking at the situation and trying to match up what's going on. Pause the video while you do that and we'll check the answers in a second. Okay, so going through them in the numbered order then. Number 1 is going to be B, because if we look, we've got a shallow section to start with, but the gradient is increasing, the slope is getting steeper. That means we're speeding up, and then we have a constant speed section. So the only scenario that corresponds to is the car accelerating up to a steady speed. Accelerating is often used to mean speeding up. We'll talk in a later video about the exact definition of accelerating. But if the word accelerating is used in the description, it's often refers to the speed increasing. So speed increases and then stays constant is a car accelerating up to steady speed. Number 2, well, the first section of this graph, although it has a value for displacement, is horizontal line, so that means that the object is not moving. And then the straight line section means at steady speed. So the only situation that corresponds to is D, the boy sitting still on a chair and then walking away steadily. So he's sitting still during the horizontal section and then walks away steadily during the straight line section over here. Number 3, Well, it kind of looks like it should be this, because really what we're doing with this graph is kind of looking at what the flight looks like as you throw something, and indeed it is the ball being thrown in the air. If you think about it, if you throw a ball upwards, it moves up fast to start with, but then as gravity acts on it, it will slow it down. So the gradient is gradually decreasing until we get to the top here, where for an instant it's kind of stopped at the top, okay, and then it falls back down again. Its displacement decreases, and the gradient's increasing. It's getting steeper and steeper as it falls back down and speeds up. Okay, so that is definitely number A, and that means that 4 has to be the only option left, which is C. Cyclists moving at steady speed, then braking to reach a slower steady speed. So we have a straight line section, which is our first steady speed, and then we gradually decrease in speed in the curved section, and then a shallower section, again a straight line, for our slower steady speed. Okay, so that's the basics of distance time and displacement time graphs. Now we're going to go on to a section which is really only for higher tier, which is actually getting some numbers from these graphs for speed. We've talked about fast and slow and which direction things are moving in, but if we actually need to do some calculations about how fast things are going. So if we look at a fairly simple graph for a distance time graph over here on the left hand side, we have two sections A and B. And all we need to do is to calculate the speed is to get the numbers from the graph to stick into the formula. So I'll show you this for a few examples, and then you can try and do one for yourself. So section A over here, well, the speed is distance divided by time. So during section A lasts 20 seconds, this straight line section here. So if we look, the little green arrow on the bottom here indicates that we've gone from 0 to 20. So for all of these sections, if we want to find out how long they are, we just take the end time and subtract the start time from it. So 20 minus 0 gives us 20 seconds. And similarly, we take the end distance and subtract the start distance from it. So we end up at 4 meters, and we started at 0, so that's 4 meters, straightforward. So 4 divided by 20 gives us 0.2 meters per second. Okay. And section B, again, you've got to be slightly careful here. Remember, we're only interested in the distance travelled during section B and the time taken during section B. So section B runs from 20 to 30 seconds, so it's at 10 seconds in total. And we go from 4 to 10 meters, so we've travelled 6 meters in total. So distance divided by time for section B, 6 divided by 10 is 0.6 meters. Remember, when you're doing this, to make sure you're reading off the scale on the graph, a very common mistake is just to count the squares. And if the scales aren't even, you will equal to each other, then you'll get a problem there. Okay, so you must use the actual scale, not just count the squares. Okay, and then this is really a sort of higher tier plus thing. It doesn't really specifically mention this on the syllabus, but it's very closely connected. And for a sort of high-end question, they could ask you this. We're looking now at a displacement time graph and how to get velocity from a displacement time graph. And again, the velocity formula is not on the syllabus, but really velocity is change in displacement over time. Okay, so we do the same kind of thing. Section A here, well, 15 seconds and a change in displacement of 8 meters gives us plus 0.53 meters per second, and it's plus because our displacement has increased during section A. Now, during section B, our displacement has decreased, so we're going to have a negative velocity. So sure enough, if we use our value at end minus value at start rule, then we get a displacement of 4 meters at the end, and we started with a displacement of 8 meters. 4 minus 8 gives us minus 4 meters. And our time for that section goes from 15 to 35 seconds, so it's 20 seconds in total. So displacement divided by time for section B is minus 4 divided by 20, giving us minus 0.2 meters per second. And again, you can see the things make sense because section A is steeper, and the size of the velocity, the speed, if you like, 0.53 meters per second, is larger than for the shallow section B, which is 0.2. So it all kind of makes sense. And then the last thing is to look at how to get the average speed from this. So in the first video we looked at average speed, which is the total distance divided by the total time. So all we care about here is the very end point and the very start point. It really doesn't matter what happens with the red line in between. It could wiggle all over the place. As long as we end up at the same point, we'll get the same average speed. So we're just looking for the total here. We've done a total of 10 meters, and in a total of 30 seconds, 10 divided by 30, 0.33 meters per second. Again, rounded to 2 decimal places is probably a sensible number to use. Okay. And similarly for the, again, not strictly on the syllabus, but the average velocity, if you were after it, would again just be the total displacement change divided by the total time taken. So for our displacement time graph here, we have a 4 meter change in displacement, and it's taken 35 seconds for that to happen. So our average velocity is 4 divided by 35, and that should say plus 0.11 meters per second, because we have ended up in our original travel direction away from where we started. We're 4 meters away in the positive direction. Okay, so last thing then is for you to have a go. Just calculate the speed for each section of this distance time graph and the average speed for the whole journey. We're not going to do the displacement time graph because, strictly speaking, it's not on the syllabus. But if you can do the distance time graph, then the displacement time graph is very similar. So pause and have a go at that, and we'll go through the answers in a sec. Okay, so the answers to this then are section A. We've gone 8 meters in 10 seconds, so that's 0.8 meters per second. Section B, well, it's stopped, so we don't really need to do any calculation. It's horizontal, so we know it's stopped, which is 0 meters per second. But if you think about it, we've gone 0 meters in 20 seconds, so 0 divided by 20, if you just blindly stick the numbers through, still gives you 0 meters per second. Section C, we've gone from 8 to 12, so that's 4 meters, and it's taken us 30 to 60, so 30 seconds to do that. So 4 divided by 30, 0.13 meters per second. And finally, section D we'd expect to be quite fast again because it's steeper. And if you look, it's exactly the same as section A, really. We've gone 8 meters in 10 seconds, so we get 0.8 again. And then finally, the average speed. Remember, don't fall into the trap of averaging all the sections. That won't get you the right answer. The average speed is, we've got a total of 20 meters in 70 seconds, giving us 0.29 meters per second. Okay, so that's some graph calculations for distance and displacement time graphs, and that's the end of this video.